All right, let's get right into it. Today, we're diving deep into the heart of chemistry, chemical bonding. These are basically the rules of connection that build, well, everything in the universe, from the water you drink to the DNA inside your cells. So, let's jump in.
It really all comes down to this one big question, right? How in the world do atoms stick together? What's the actual glue that holds our entire world together? Stick with me, and by the end of this, you'll have a crystal clear answer. So the main idea here, which we can thank scientists like Slater and Pauling for, is something called orbital overlap theory. And honestly, the best way to think about it is like a handshake between two atoms. For them to form a bond, their electron orbitals have to literally overlap. Now, when this overlap happens, something really crucial occurs. It pulls all that electron density, that negative charge, right in between the two atoms' positive nuclei. And that shared cloud of electrons is basically the superglue holding them together in a nice, stable bond. But, it's not just a free-for-all. There are some ground rules. Only the outermost or valence orbitals get to play. The electrons they share have to have opposite spins, and here's the key takeaway. The more they overlap, the stronger the bond. This is exactly why a pp overlap is way stronger than an ss overlap. See, p orbitals are kind of lobe-shaped and directional, so they can get a much better, more direct overlap than those round, non-directional s orbitals. Okay, so we know bonds are all about that overlap. Now, let's meet the two main types you're going to see everywhere, sigma and pi bonds. You can think of them as a direct, head-on connection versus a parallel, side-by-side connection. This table lays it out perfectly. A sigma bond, that's your strong, direct, head-on collision right between the two atoms. It's always the first bond that forms. Pi bonds, on the other hand, are a bit weaker. They're the side-to-side overlaps that happen above and below that main sigma bond axis. You're only going to find these guys in double or triple bonds. All right, so we've established that atoms are sharing electrons. But is it always a fair, even split? Oh, no way. This is where we get into a full-on electron tug-of-war. We call this property electronegativity. It's just a measure of how badly an atom wants to hog those electrons. Just take a look at this chart. It shows you the whole spectrum. On one end, you've got a hydrogen molecule, HH. The two atoms are identical, so the electronegativity difference is 0. It's a perfect, even share. That's what we call a nonpolar covalent bond. Then you look at something like HCl. Chlorine is a real electron hog compared to hydrogen, so it pulls those electrons closer. That creates a polar covalent bond. And then you get to the extreme, like sodium chloride. The difference is just massive. Sodium basically gives up, and chlorine just snatches the electron entirely. That's an ionic bond. And we can actually put a number on this lopsidedness. It's called the dipole moment. Think of it like an arrow. The length of the arrow tells you how polar the bond is, and the direction it's pointing tells you which atom is winning that tug of war. And here's what that looks like in hydrogen chloride. See that arrow? It's pointing from the less electronegative hydrogen straight to the more electronegative chlorine. It's literally showing you where those shared electrons are hanging out most of the time, creating a little bit of a negative charge on the chlorine and a little positive charge on the hydrogen. So we've seen even sharing and uneven sharing. But what about the really weird cases? Let's dive into a couple of special types of bonding where the rules get even more interesting. First up is the coordinate or dative bond. Now, this is still a covalent bond where electrons are shared. But get this, one super generous atom brings both electrons to the table. It's like one friend brings the entire pizza to share with another friend who didn't bring any food but has an empty spot at their table. The first atom is the donor, the second is the acceptor. And then you've got metallic bonding, which is a whole different ballgame. Seriously, picture this. You have a neat grid of positive metal ions, just kind of floating in this massive sea of electrons that are zipping all over the place. These electrons aren't tied to any single atom. They're communal property. And that mobility, that freedom to move, that's exactly why metals are so good at conducting heat and electricity. Okay, all this theory is fantastic, but how do we actually use it? How do we sit down and map out what a molecule looks like on paper? For that, you need a blueprint, and that blueprint is the Lewis structure. Now, don't let this list intimidate you. It's a super reliable 6-step recipe that works almost every single time. Just follow it in order, from 1 to 6. And that last step, assigning formal charges, think of that as your quality check. It's how you make sure you've built the most stable, most likely structure. It's like balancing your chemical checkbook. All right, let's put this into practice. We're going to build the nitrate ion. That's NO3 minus. Step 1, who's the central atom? Well, nitrogen is less electronegative than oxygen, so it goes in the middle. Step 2, let's count up our electrons. We've got 5 from nitrogen, 3 times 6 is 18 from the oxygens, and don't forget, 1 extra for that negative charge. That gives us a grand total of 24 electrons to work with.
Okay, so we'll start by connecting the nitrogen to each oxygen with a simple bond. That's 3 bonds, so 2 electrons each. That's 6 electrons used up. We've got 18 left. Now we'll sprinkle those 18 electrons around the outer oxygen atoms. Okay, so now each oxygen has a full octet of 8 electrons. But wait, take a look at that nitrogen in the middle. It's only got those 3 single bonds. That's only 6 electrons. We've got a problem. Its octet isn't full. So, how do we fix this? Simple. We go to one of those oxygens, grab one of its lone pairs, and swing it down to form a double bond with the nitrogen. And voila! Now nitrogen has its octet, all the oxygens still have their octets, and we have a perfect, valid Lewis structure for the nitrate ion. Whew! Okay, that was a lot to take in, I know. So let's do a quick, rapid-fire recap of the biggest takeaways, the stuff you absolutely need to remember for your next exam. First, bonding. Covalent bonds, it's all about orbital overlap. The more overlap, the stronger the bond. Sigma bonds are those strong head-on connections. Pi bonds are the weaker side-by-side ones you see in double and triple bonds. And polarity, that's just the result of that electron tug-of-war, which we measure using the dipole moment. Next, structures. Remember, a coordinate bond is where one atom donates both electrons. Metallic bonding is that classic sea of mobile electrons. And for Lewis structures, seriously, just trust the process. Follow those 6 steps every time. And please, please, please don't forget to add or subtract electrons if you're dealing with an ion. And there you have it, your complete guide to the fundamentals of chemical bonding. Now I've got to ask you, what's the absolute trickiest, most annoying Lewis structure you've ever had to draw? Let me know down in the comments. Thanks so much for watching.